Turing tests, Harness rooms. You have learned about types of AI evaluations. That's all right. Okay, very good. So you do revision, ah? How come you can remember one? Based on my experience, student, don't know. They can't really remember. Okay, very good. So yeah. So let's move on to this new chapters, chapter two, prop applications and okay, problem definition and problem solving. So testing. Testing. Okay, so these chapter twos are actually uh, combined with chapter 3 and chapter 4. So this chapter 2, they are actually considered one topic, which is search applications. Okay, so whatever search applications, for example, Waze, Google Map. So you have this sliding puzzle. You have a cannibals and missionaries case. You have a magic cube. Okay, so these are the example for searching applications where you need an application algorithm to help you to find the optimal solutions. Okay, so there are some examples we are going to show you later on. So chapter 2 is more towards on the goal and problem formulations. Okay, meanwhile chapter 3 and chapter 4 are about the algorithms. Okay, so anyone from diploma? You learn about preferences? Huh? Yeah. You didn't take AI. So anyone take AI in diploma? And we have this early exposure of AI in diploma. If you take that course, then you probably have learned this. The algorithms of the search. For you have a blind search, and you have a heuristic search. Okay, if you have already learned this in your diploma, it's okay. You just take it as a revisions. Otherwise, it's okay. It's something new to you, right? If you have already taken, then just take it as a revisions and just revise. We have some example exercises here. All right. So okay, so this is the learning outcome of today's lessons. You're going to formulate the goal and the problems. Alright, so there are 3 important stages to find the optimal solutions for any of the search applications here. The first one is you have to formulate the goal, right? You have to identify your destinations, your abstractions, your optimal solutions. Moving on to the problem formulations, we have 7 elements going to cover later. Then only we decide what algorithm to use. You're going to use heuristic search, are you going to use blind search and others? So these ones we will cover in the next lessons, next week and 2 weeks later. Don't worry about that. So we have this heuristic, how do we apply the search to find the optimal solutions. So but today's we will just cover goal and the problems, which are these 2 topics. Okay, so inside the goal formulations, there are 3 very important elements here. Alright, so the first one is the goal. This one is the outcome. What is your destinations, right? So you have to identify. So from now onward, this everything that defined here is not only for you, it is for the agents, it is for the machine, right, to find the optimal solution based on the information that you key in. So I'm going to show you an example later. Alright, so goal is what is the outcome, what is the destinations, optimal solutions, what is the best solutions. Do you want to reach your destination in the shortest distance, or do you want to reach the destination in least number of time? So you have to define properly. Okay, so shortest distance doesn't mean that you're going to reach in least number of time. So yeah. Okay, and then we have the abstractions. So abstraction in other definition is what are the unwanted informations? Unwanted informations that you can ignore. Okay, so that you can focus to find the optimal solutions. Okay, I repeat again, what is abstraction? It is actually the unwanted information that you can actually ignore, remove, so that you can focus to search your optimal solutions. In other words, it's the scope. For example, you would like to reach from here, TAR-UMT to, let's say, KLCC. So in shortest distance. But you couldn't say that, okay, I want to reach the KLCC in the shortest distance, at the same time, least number of time, at the same time, I don't want to have any toll, at the same time, this and that. So you can't have the perfect conditions. Right? So you have to set the scope. It's not practical, so you have to set the scope. Okay, I would like to reach the destination in the least number of shorter distance, but at the same time, I don't really bother the time taken. Okay, at the same time, I don't really bother the how much toll that I'm going to pay. Right, so you have to give and take. So on the scope, you have to limit the scope. Okay, so I'm going to give you some examples here. So this is the ways, right? So you have the destinations. So in this case, the destination will be Sendai Velocity. Then after that, you have to define your optimal solutions here. So the optimal solution here, you can see that you have several optimal solutions. The first one is the least number of time, 70 minutes, but it takes you like 11 kilometers. But then you have a third choice here, where it gives you the least so-called the shorter distance, 10.2 kilometers, but however it takes a longer time, 20 minutes. At the same time, you have to define your abstractions, which is do you want to avoid the toll, avoid ferries, and so on and so forth. So you have to define this before the problem formulations. So look at this state space, another examples here. Okay, so assuming that you have this state space showing all the possible paths that can travel from your initial state, which is TAR-UMT, to the KLCC. Okay, so you want to travel this from here to KLCC to enjoy the night view, let's say. So you have three possible paths. The first one is you directly from the TAR-UMT to KLCC, it takes 15 kilometers. The second path will be the TAR-UMT, you travel, you have to pass through this Wangsan Maju and reach the KLCC. It will take 3 kilometers and 13 kilometers. And then the last one will be you pass through the Diwangsa, 6 kilometers, and you go to the KLCC, it's 8 kilometers. So that is the state space showing all the possible states, all the possible paths that can reach the KLCC from the TAR-UMT. So let's define the goal. So remember, you have three elements in the goal formulations: goal, optimal solution, and abstractions. So in this case, what is the goal? KLCC. Very good. Okay, so goal KLCC. Optimal solutions. What is your optimal solutions? You can define from here. Yeah, you would like to reach the destinations with the shorter distance. Okay, abstractions. What are the other factors that may affect you to reach the optimal solution, but at this moment you limit it, you don't really bother? Okay, very good. So you can say time taken can be ignored. The time is not your concern right now. You just focus on how to reach the KLCC in the shortest distance. Then it's called 3 marks. That is the 3 elements. Simple. Okay, very good. So let's move on to this problem formulations where you have 7 elements here, which is the initial state showing that what is your starting point. Right? You have a destination, definitely you have an initial state where you need to code in your program later. You have a state space, as I mentioned. State space is actually a space showing all the possible paths that is started from the initial state. Path, it just simply show the sequence of actions, how the path is showing from one state to another state. A path cost is a total cost taken to travel the path. The successor, which is the most important elements in the problem formulations, that if you define this successor function wrongly, then your agents may reach the wrong destinations. I'm going to show you some example how do you define the successor functions. Goal test is to test whether the current state, or every time you expand, you do the search, every time the agent search, then is it equal to the goal test? If equal to the goal test, where we have to stop the search. And lastly is the step cost, where the step cost is the cost taken from one state to another state. Path cost, meanwhile, is the total cost taken along the path. Alright, look at this same examples again. So in this case, which one is your initial state? TAR-UMT. Okay, very good. So your initial state is TAR-UMT. you can just write TiUMT, or this is just representations on how you going to code inside the program. So don't worry about this. You can just put go, you can just put move. Alright, so that is the starting point, TiUMT. So you're going to travel to the next station, but you just want to display this is the initial state. That's why I put 0 here. Okay, so the next one will be the successor function. So successor function, so you have to understand first what is successor. So assuming that you have a state here, A, okay, A travel to B. So this B here is actually your successor. Okay, or we can call it as a child node. Or we can call it as a, it's actually, we will call it as a successor, or it could actually call it as a child node. So this one will be called as a parent node. Okay, so this is a successor. So what does it mean by these successor functions? It's basically functions to generate the successor from a current state. Okay, I repeat again, what is successor functions is the functions that will take the input and generate all the possible outputs. Right, so you have to remember that how agents do the search. So you have to provide the successor functions so that whenever agents do the search, it will go to the successor function and look for the possible actions. Oh, I should go this, so I should go to the C. So in this case, the TiUMT, let's say we take this case, TiUMT. So we can say that TiUMT can move to KLCC. So this is one of the possible actions, one of the successor functions. You can also say TiUMT can travel to Wangsa Maju. Another possible actions, TiUMT can also move to Titi Wangsa. So these are the 3 possible actions for TiUMT. So whenever we do the expansion, let's say this is A is a TiUMT, then the agents will go to this successor function and search. Oh, TiUMT can go to KLCC, then they will expand the search. Okay, so it's actually basically functions to guide the agents where to go now. Okay, alright, so don't worry, we have some example later on. So state space, as I mentioned, is just basically a space consists of all the possible states. For example, we know that TiUMT can travel to KLCC, Wangsa Maju, and Titi Wangsa. So from here, we would have another search tree showing TiUMT can go to KLCC, Wangsa Maju, and Titi Wangsa. From Wangsa Maju again can travel to KLCC and also TiUMT can travel to KLCC and TiUMT. So you're going to keep expanding. So that will be the state space. It's a space consists of all the possible paths that started from the initial states. Okay. So the next one will be the path. It's showing the sequence of states connected by the sequence. It's basically just how are you going to display the sequence of actions from one state to another state. So in this case, just like the ways, you're going to see that how you can actually move from your initial state to the go state by showing the sequence of actions. Alright, and then you have a go test. It's just to show check whenever you do the expansion. Whenever A expand to B, you have to go to another function. Check, is it B equal to the go? If B is equal to go, then we are going to stop the search. If not equal to go, then we have to continue the search. Alright? Oops. Alright, and then we have this stack cost. Yeah, stack cost is just showing the cost that travel from one state to another state. In this case, TiUMT to Wangsa Maju, the cost is equal to 3. So always remember the cost is actually depends on how you define optimal solutions. Okay, the cost, it depends on how you define optimal solutions. If your optimal solution is to reach destination in the shortest distance, is about distance, then your cost will be 3 kilometers. If your optimal solution is to reach the destination in the least number of time, then your cost will be seconds, minutes, hours. Alright. So, and the last one will be the path cost, right? Path cost is the total distance. For example, time Yanti travel to Wangsa Maju, travel to KLCC. What is the total cost travel along the path? So you 3 add with 13, you will get 16. That is the path cost. Okay, so is that clear? So we have how many elements in Go formulations? How many elements in Go formulations? 7. That one is problem. Go formulations. This. This, and this. You have 3 elements in Go formulations and 7 elements in problem formulations. So let's look at 2 examples here. Okay, this is a summary. You have 3 elements here and 7 elements under problem formulation. So look at this passive questions. It's a very famous questions either in a midterm test or final examinations. An intelligent system is designed to search for shortest path from S to G. Right? Video 1 shows directed graph. Directed graph means that it's only one direction. If you look at the example that I show you now, is actually bi-directions. So this one is unidirections. It's one directions only. Right? S can go to A, but A cannot go to S. So you have this table 1 show Euclidean distance. But at this moment, forget about this table 1. So we're not going to learn the algorithms. You're going to use the A star, then you have to use table 1. But at this moment, forget about this. Just focus at this table. Just focus at this figure 1. Alright, formulate the goal. So what is the goal? S. S is it? What is the goal? G. Okay, very good. What is the optimal solutions? Okay, right, to reach the G with the shortest distance. Okay, what is the attractions? Again, time overcorrect. Okay, times weathers, weathers. You're not going to bother if the weather is like raining days. It may affect the speed, everything like. But you don't really care what is the weather. You just want to focus on how to reach in the shortest distance. Very good. So how about the problem formations? Initial state. What is your starting point? S. What is your successor functions? Okay, so you can write. Okay, successor function is actually functions used to generate a successor. Okay, so for examples, just now someone say A to B. Some more. A can go to B, or A can go to C, right? A can go to B, A can go to C. So S, how about S? S can go to A or AB. So B can go to D. That's it, right? Then C. So you have a lot of successor functions. It's possible. It's all the possibles of movement for the agents to move. So meaning that when the agents start to search, where's the optimal solutions? Where if the successor at S here, then he will go to this successor function. Find I can go to A or go to B. I can do option here. Then now the agent is at the A. So A will go to successor function. A can go to B, A can go to C. A can go to B, A can go to C, and so on and so forth. It's basically a functions to tell the agents where to go. Where is your next move? Okay, so very good. So you know the successor function now. So what else you need? Wing Yi. Am I correct? What else? Path. Okay. So before the path, there's one more very important one, state space. Yeah, I'm talking about state space first. State space. Okay, so state space is basically all the possible paths that's starting from the initial state, right? So I'm going to draw the state space here. So let's say we start with S. S, you can go to the A and B, right? Let's look at the A first. A can go to B and C. Okay, B and C. Okay, B can go to D. Okay, so B, what else? B can go to D again. Okay, C can go to D and E. Okay, D can go to A and G. Okay, D again can go to A and G. Okay, D can go to A and G again. E can go to F. A can go to BC again, and so on and so forth. So you found out that you are actually keep trapping inside a loop, right? A can go to T. So don't worry, but at the end you are going to learn that how are you going to avoid this repeated state. So in the search algorithms, we always remember you have to remove the repeated state, as it's going to waste your time and also the memory. Okay, but that is the state space partially state space. Okay. So done. So we have what else? Someone say path, right? Path is a sequence of actions. So for example, you have a lot of path here. You can give one example as go to A, this is B, this is D. Yeah, so how are we going to display the path on the screen or to the user? What else? 1, 2, 3, 4. Go test. Yeah, go test. Test if current state is equal to go state. Okay, so for examples, if the current state is equal to, what is the goal? Is equal to stop and then return, maybe path cost. So meaning that the agent will start to search. Okay, A search to A. So check whether is it A equal to G or not equal to G. I continue the search. Or B is it equal to G? Not equal to G. Continue. So you should have these functions in your code later. I'm going to show you the code later so that you can get a picture. Why do you need to learn all these things? What else? Start cost. Okay, start cost. So you can give example, start cost, let's say S to A. So what is the kilometers? S to A, 3 km. Also you have a path cost. So you can give whatever path here, let's say S to A to B, B to D. So this one S to A is 3, right? A to B, 2. 5. B to D, 3. So the path cost will be, so 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7. Yeah, done. That's it. That is how you define your goal and problem. As simple as that. Then you score 8 marks here. But based on my experience, students lost a lot of marks here. They managed to get the goal formulations, but come to here, yeah, blank. Okay, the mark breakdown is, this is 3 marks here. So here you can actually choose 5. can only choose 5 to formulate, right? You can only choose 5 of it. You don't really need to write everything. But I think this is back to 2 years ago lah. If you look at the recent one, we don't really ask you to memorize all these terms. We do provide to you, like okay, formulate the initial state, go test, start cost, and path cost. We provide the terms instead of asking you to memorize it. In this case, formulate, go, and problem means that you have to remember all these terms, right? But in the latest one, in the recent years, past year, there is a terms given. Okay, right. So let's move on to the next questions. Another partial questions also samples. Forget about this 7430 is actually another heuristic course. We're going to use it for the heuristic search, okay, which is the additional information to do the search. But by looking at these questions only, right, an intelligent system again search S to G. So shows the graph of 7 stations. Okay, it's the both above. Alright, so same, right? Your goal is G, optimal solutions, times, yeah, it's largely the same. Just I think the difference will be the successor functions, state space, stack cost, and the path cost. The remaining will be the same. Right? So it's not inside your slide, yeah? Not inside your slide. I'll give you 5 minutes. Do you want some time to try this question out? Yeah. Just like me, sequence of action. It doesn't necessarily repeat the hit and close. Just the up. Just like the waves are. How you display the path? How you want to show state by state together with the kilometers? Yeah, partial path. Go over here. Okay, is that clear? Okay, while you are still writing, maybe you can take a rest for 5 minutes. For those you want to take a break. For those you still don't understand, you can come down and ask me. I would say that will be should be famous questions in final examinations, and I hope that you guys can score as many as possible for question 1 and question 2, because for question 3 and question 4 will be a little bit tougher, will be very tough, so you may lose a lot of marks for question 3 and question 4. So question 1 and question 2 is the place for you to score the marks, to cover the question 3 and question 4. So please do understand this and practice. Okay, so we may take a rest for 5. Yeah, you can go to the washroom.
真的有查到这个东西，真的有查到这个东西，这个东西。
我就没有查。
是，我没有查题目，反正他就是要看这个东西。
我就讲 skip，你要 skip。
ไม่ได้พูดนี่หรอกับ
AI。
ไปต้น
这写作我的原因，为什么我不去？那我的原因说，那3D主要拍摄会给他顺利一点。I'm like，
他今天真的很好玩。你去哪里？等一下，等下你去隔壁。去。
After you get
Sorry baby，妈的，那种颜值狗，开得到我的家，对不对？我一插进去，看到，然后我就开这个，也没错。
哦，这一看哦。
睡觉了。
我不吃，我不吃，你拜关了吗？拜，他是我同事，吃。
Okay, lot of time from you. Right, so let's continue with the next examples. Okay, we're still in this problem and goal formulations. So let's move on to the next examples here. It's called Mysteries and Cannibals. Anyone playing this game before? No. Yes, sir. How are you? So it's my F. Sorry, if you have never played this before, so let's play this together. Okay, so the ideas of this game is very simple, where you would like to fetch, okay, these 3 cannibals and 3 missionaries from this left hand side to the right hand side. So these 3, these left hand side ones, we call it as cannibals. These are cannibals. So they are people that will eat people. They will eat other people. So we have these 3 black search ones. They are known as missionaries. Just a normal people. Okay, so we have 3 cannibals, 3 missionaries at the left hand side. So you have to think away how to put them, all of them, from the left hand side to the right hand side. Okay, but there are some rules here. The number of cannibals must less or equal than number of missionaries. In other words, missionaries must be more than cannibals, because otherwise the cannibals will eat the missionaries. Okay, no one is allowed to swim, right? And then the maximum number of people that can be on the board will be only 2. Okay, so let's move on to this again. So be clear of the rules. All right, anyone would like to start first? 2 cannibals. Someone cannibals. Okay, after that, so the board is already at the right hand side. Yeah? So you have to think how to so-called bring that board back to the left hand side. 1 or 2 come back. 1 come back. Okay. Testing. 2 cannibals. Sure. 2 normal. 2 cannibals. Someone said, oh.
Okay.
Huh? So you still insist 2 cannibals, huh? You? Oh, not confidence already.
1 and 1.
1.
1 and 1.
1 and 1. 1 1. 1 1 sure. 1 1 go there die already. We go. Tables cannot more than number of missionaries. I can reset. So just now is 1 1, is it? 2 2. Okay, 2. 1 come back. 2 cannibal. 1 come back. And you don't just so fast to reveal the answer. 1 come back. 2 go there. How? Oops.
1 1.
Oops.
1.
This is not you want. I think you still managed to get an answer. Can, huh? Yeah. 1 1. Anyone agree 1 1? 1 1. Okay, one cannibal, one missionaries, go back.
好像是一样的东西的。又是一样的东西。Same shit 呀。
Let them fight first. Two. Yes. Next move.
One.
Too normal, too normal.
Don't know.
Too normal.
One.
What is too normal? Normal what?
Missionary.
Missionaries. Oh, okay. They are called as their name is missionaries.
The one that don't kill.
So this one is not normal lah.
Do you see anyone eating their own kind? Is that considered normal?
Still respect them lah. So they are called cannibal and missionaries lah. Okay. So someone say what? Two?
Two missionaries.
Two missionaries. Okay.
One cannibal.
Oh, okay.
One by one.
Oh.
Hey.
Very good. Okay, so we can try another rules where now you can fetch 3 people per treat. Okay, how? 3. Now you can have 3 people instead of 2. So meaning that it will be simple compared to the previous case. 3 go there. 3 come back. 养车河. 3 go.
Okay.
Cannot. This one cannot. Okay.
3 go there.
3 cannibals.
3 cannibals.
1 come back. Okay, 3 go. Okay, 1 come back. Okay, see? It's much simple. Because you can fetch 3 people instead of 2. Yeah. So what have you learned from this game? So what lesson that you can learn is actually without any strategy, what we are going to learn next week, which is the heuristic search or blind search. We just try and errors, right? You just try 1, you try 2, and then die, you reset again. So yeah, so you will see that next week we have certain rules and certain strategies so that you can actually avoid all these mistakes. You can just use the solutions that given, and then you reach the optimal solutions. Okay? Yeah, very good. So now come to the most difficult part where you have to design the goal and formulations before the strategies. Okay? Okay. Alright, so what is the goal? So before we continue with goal, I think it's better for us to represent this graph, this so-called graphics into some list first so that you can actually reuse the list during the search. So maybe we can represent it using, you have a left hand side and then cannibals. So this is left hand side. So this is cannibals. So LC is stand for the number of cannibals at the left hand side. Then we have number of mercenaries at the left hand side. We have a board positions, is it either in the left hand side or right hand side. And number of cannibals at the right hand side. And number of mercenaries at the right hand side. Okay, easy. Right. So we represent this graphic into some representation first. Alright, so after that, okay, then we can come to here. So what is the goal? So you write to move all the 3 cannibals and mercenaries to the right hand side, right? So how to represent it is to become 0, 0, 0, R, 3, 3. You become number of cannibal and mercenary at the left hand side, 0. The board must be at the right hand side. There are 3 cannibals and 3 mercenaries at the right hand side. Okay, so it's easy to understand, right? So we represent this in this form first. Okay? Alright, so what is the optimal solution in this case? you write to reach the destination, or you write to reach the goal using least number of trip. Right? I will consider this is one trip, come back another trip now. Right, so I write to reach the goal using least number of trip. Make sense, huh? Okay, abstractions. Time. Okay, now time is considered. So you don't really bother about the times as long as you reach using the least number of trip. Weathers is another factors, but you can also ignore. So weather could be one of your abstractions. Okay, initial state. What is your initial state? Okay, very good. It become 3, 3, L, 0, 0. Yeah, good. Alright, so now what is the successor functions? So remember, it's refer to possible actions to the agent, right? So can you tell me what are the possible actions when the boat is at the left hand side? If the boat is at the left hand side, so what is the possible movement? Let's say this is cannibal, this is missionary. It's at the left hand side. Okay, so what are the possible movement? Okay, you can move one cannibals from left to right, right? Okay, so you can say you can move one cannibal from left to right. That is one of the possible actions. Any more? 2C, move to the R. Very good. Maybe 3C. 1M, 1C to the right hand side. 1M to the right hand side, or 2M to the right hand side. Any more actions? No more, right? You can only move one. Yeah. Okay. Oh yeah. Move one to right hand side, 2 to right hand side, 1, 1. Yeah. No more. Huh? Given that the boat can only fetch maximum two people, in this case. If you have 3 people per maximum, then you will have different successor functions. Okay? But what if, let's say, the boat is at the right hand side? Then you can have 1C to the left, 2C to the left, 1M, 1C to the left, 1M to the left, and 2M to the left. So this one, anyone not clear? Why is 1C? Why 1C to right or 1C to left? So I assume all good. Okay. So that is in the layman terms where we can understand, oh, you move. But in the coding later, you can't just write 1C, the program cannot understand. So you have to write, for the first case, I'm taking the first examples here. So you know that is the representations, right? So you're going to move 1C to the right hand side, meaning that the cannibals, you have to minus 1. Correct or not? This is actually refer to the numbers. So if you move one cannibal from left to right, it means that you have to minus 1. You have to minus 1. So this is LM. LM do nothing because you're not going to move any missionaries. So the boat will be at the right hand side. This is LC plus 1 and then LM. So this is how you're going to code inside the program, and this is layman terms. Okay, either way is okay. You can write. You can write in this way, or you can write in this way. Doesn't matter. Okay. Okay, maybe I'll show you this. Give me some time. Okay, so this is the code for this case, miscellaneous cannibals. As you can see that we have to define like what is C left, what is M left, and then what is the goal state. So the goal state is as long as your number of cannibals on the left hand side and number of missionaries on the left hand side is equal to 0, then it's going to go state. That's why I say is that you have to define all this before you write the code. So you have to then we have to convert this into the codings. And then this is the validations. Make sure that your board cannot more than 2 people and so on and so forth. You have to put it here. And then that is the successor functions. So you have to define all the possible movement for this case. How the books can be moved from left hand side to right or right to left. So in this case, if you want to move the missionaries, 2 missionaries from left to right, then this is how you have to represent it, right? So you have to -2, and then at the right hand side you have to add 2. And now the board position will be at the right hand side. Okay, so if you don't understand this, it's okay. So this is not very important. Yeah, forget about this. I just want to show you make curious that why we need to learn all these things, because you have to give instructions to the agents. So this is how we instruct the agent to do the task for us. Okay. Yeah. So if you have time, then you probably can go through this. So this is inside your practical tool here. But but under me, I'm not going to cover this practical because it's not inside your assignment. Okay, but that's the theory, that is the practical. Okay, so next will be what? State space. So state space will be a little bit okay, so I draw that now. So you have let's say a 3, you have left 0, 0. So the first one, you can actually move, if you follow the successor function, move one cannibal to the right hand side. So it becomes 2, 3, white, 1, 0. Okay, so you can also move 2 cannibals. It becomes 1, 3, white, 2, 0. You can also move 1, 1. It can become 2, 2, 1, 1. Okay, then continue when the board is at the right hand side, you can move 1 cannibal back here. Okay, so this one, you can move 1 cannibal to here. Okay, you can move 2, then you back to the original state. And so on and so forth. So you have to continue expand until there is no more solutions or is that end. That will be your state space. Okay, so means that you have to keep find from here, can go to this state, can go to this state. So you have to take note on these positions. Now at the left hand side, now at the right hand side. So you have to try those. So how the boat move? So I'm not simply draw this out. I always follow this successor function. So at this moment, the boat at the left hand side, what is the next move? You can move 1 to the right hand side. So that's why I move 1 to the right hand side. I can also move 2 to the right hand side. That's why I move 2 to the right hand side. I can also move 1, 1 to the right hand side. That's why I can move 1, 1 to the right hand side. But you look at here, I cannot move missionaries because once you move missionaries, the number of missionaries at the left hand side is always lesser than the number of cannibals. They will be eaten by the cannibal. So that's why I didn't continue with these 2 moves because it's not valid. Yes, it still counts as successor. Maybe until at one point where you have a number of missionaries more than cannibals, then you can perform these two successors. Okay, so don't worry, is it whether it's valid or not? You just list it down all first. Then in the code later on, you have to put a validation. Make sure that the number of cannibals is always lesser or equal than the number of missionaries. No. You can have this. So when you do the movement, then you have to in the code you have to add the validation. Make sure that it's follow the rules. Okay, so that's the state space done. So path, you can just provide any of the examples. You can put LL. Okay. So this is example of the path. You can travel from here, travel from here. The path does not necessarily you must reach the goal. No, it's just example of the path. Okay, goal test is to test if is equal to goal. Is the current state is equal to 0, 0, 3, 3. If yes, then stop. Start cost in this case is definitely 1 because you are going to move 1 to another levels is 1 3. So that is equal to 1. So the path cost, if I use these examples, is become 1 plus 1 is equal to 2 trips. Okay? We're still human lah. I mean, you don't have such questions that you will take like 1 hour to solve. You know? We will try to control where students manage to solve all the questions within 2 hours. Let's say got this kind of question, you just care and then you just walk away. So before we set the question, we actually will try ourselves whether we have managed to solve it in 2 hours. No. Okay, so are you clear these examples? So I hope that you have a better understanding on what is all these things and why we need to code these things, because later on we have to put everything into the coding. So we have to instruct the agents where to move and how to get the solutions. Okay. Good. Okay, I see a number of students will start to energy low. But we still have some time. Shall we continue to the next examples? Anyone still have energies to continue? Or you still another 5 minutes of rest? Rest. Another 5 minutes of rest. Okay, 5 minutes of rest. You digest this one. I will come back to the last example still. Okay?
一股酱。